Okay, YouTube, this is a video regarding how to calculate transformer turns for switch mode power supplies, and today I'm going to demonstrate how to calculate the turns and what to consider during your calculations and design. Here I have a Ferrite transformer which was taken out of an ATX power supply, which used to supply about 350 watts, and as one can see here, I got it all dismantled. First of all, to make use of these type of transformers, you have to heat them up on a lamp first. Just take a portable lamp with about a 60-watt bulb, put the transformer for about 15 or 20 minutes, and occasionally turning it over so it heats up all together. And then, after taking off the surrounding tape from here, you can easily, or with a bit of patience, try to put a scalpel here and lift off this piece first, taking care not to burn your fingers. Just take a piece of cloth or whatever to hold the transformer with, and then try to nudge it out slowly without trying to break it. And after that, it will be quite easy to dismantle the transformer. Again, starting off with some calculations, we have to consider these things. Firstly, we have to take the core area, which happened to be about 12.8 or 13, whatever it is, and it's about 10. So it's 12.8 by 10 millimeters. So that would give us an average of 1.3 square centimeters. So that's the cross-sectional area. One also has to consider the window space we have available and the bobbin length. The bobbin length here happens to be around 16 millimeters, and the space I'm talking of is the window space available here to see what can we fit in there. Okay, my transformer here is going to be wound for a 24-volt supply, okay, of around 350 watts. Okay, starting with the nominal voltage calculation here, our mains voltage, okay, input is going to be around 200 volts and 240. So what we're going to do, we're going to take the center of that, and that is a variation of about 20% up and down. So we have 240 volts minus the 200 here, which gives us 40 volts, and 40 volts divided by 2 is equals to 20, okay, which is half the variation of the voltage here from here to here. So we add up the 200 volts with the 20 volts left here, and we round up to about 220 volts. Now, using the half bridge topology, we will be needing half the nominal voltage. So the 220 volts is going to be multiplied by square root of 2, which is 1.414, and that adds up to about 311 volts. And to make calculations more simple, I'm going to lessen that 1 volt and take a nominal voltage of 310. Okay, the variation is very small and it's hardly negligible. It's very negligible, and one cannot take that into account. So the half bridge topology we are going to use half the nominal voltage, so our voltage to start with is going to be 155 volts DC. Okay, before we start designing the design frequency and everything else, we also have to calculate the window space we have in the transformer here, and this happens to be, I inserted the bobbin inside, okay, so I would have an idea of what we have here. I have about 6 millimeter on each end, okay, to play with, so that's it has to be in consideration. So I have tried out a few frequencies beforehand, just not to make this video very long. So my design frequency here is going to be 33 kilohertz, and the copper wire used is going to be 0.6 millimeter. And also, before coming up to the secondary voltage here and the primary and secondary turns, one also have to leave some headroom if the power supply is going to be a pulse modulated one, or just having one with no regulation at all. In my case, I'm going to opt for one which is regulated, which is going to use the SG3525. So because of that, I have to leave some headroom for the chip to regulate the output voltage and keep it stable at the wanted voltage. My secondary voltage wanted here is 24 volts, okay, and it's going to be about 350 watts. So considering all these things, first of all we have to get the copper wire table and check out the frequencies. The table here, we can see a lot of things from it. It gives us the maximum frequency for 100% skin depth. One has to consider also that due to the frequency being used, the current tends to travel on the outer part of the copper conductor, and for having 100% skin depth in the copper wire, not all size of wire will suffice for every frequency. So here we have a table having American wire gauge and also the diameter in inches and also diameters in millimeter for the copper wire, and also the area, the resistance in ohms per 1000 foot, and in kilometers. This doesn't concern us because it's very long. The maximum current in amperes, and also the frequency over here. So in my case I am going to use the 0.6 millimeter wire, which is the gauge 22 here. It says about 0.64, okay, and the maximum frequency is going to of about 42 kilohertz. Now, having our frequency set around here, we may also use the 0.7, but this wire may be too large and will not fit in the bobbin, considering the pros and cons, how many layers of wires I may need to put the primary and secondary turns. It will give me a bit of more thickness, and it won't fit in the window space available in the transformer. So I opted to do it with the 0.64 millimeter. This can handle up to 40 watts, no problem for us, and the wire gauge will suffice for our needs. Okay, now knowing all this, we can start with our calculations and see what we can get. Another thing I forgot to mention is the flux density and the number of magnetic lines that are going to be transformed in the transformer during operation. So the Bmax, what are we going to call it here, has to be around between 1200 and 2000 gas. Okay, so in my design I'm going to use around 1800, not to be with the maximum but not to be with the minimum, somewhere in the center, and we can round off the figures from the given formula. So the number of turns in the primary winding is going to be 155 volts, what we got from here, okay, times 10 to the power of 8 divided by 4, which is the magnetic flux for ferrite transformers here, and having a DC pulse. And this is the design frequency, which is 33,000, okay, it's 33 kilohertz, times Bmax, which is 1800, times the core area of the transformer, which I have calculated beforehand, which was 1 centimeter by 1.3, okay, and when you add them together you get a 1.3 centimeter squared. Okay, so we have to calculate this sum and get the number of primary turns. Okay, having checking Bmax, the reason is because I have rounded up the 50 turns I have here. Instead of 50.18, I've rounded up to 50 turns, okay, for the primary winding, and I calculated the sum again to see what Bmax I have. And all I did in here with the formula is I just took off the Bmax over here and put the number of turns instead of it. So our answer will be for the Bmax. So what I did here is 155 times 10 to the power of 8 all over 4 times 33 kilohertz times 50 turns times 1.3. Okay, and I got this answer, which is 155 times 10 to the 8 all over 858 and 4 zeros, and that gives us an answer of about 1806.5, which we are still in the range between 1200 and 2000 for Bmax. So Bmax at 50 turns is still okay. Okay, that's one what have to check to round when rounding off the figures. Right, so here I'm going to check the bobbin space again, and it has found to be 16.5 or whatever millimeters here, and from this side, yes, it is 16.5. I'm rounding it up to 16 millimeters, and here, so we have the diameter of the copper wire, which is 0.6 millimeters, and the bobbin space here we have is 16 millimeters, so it's going to be divided with 0.6. So now we know that we have 26.6 linear turns. So considering the 50 turns we need, in these types of transformers, it's best to have half the primary turns wound in the first place, then you wind the secondary turns in the middle, and then you put half the left primary turns on the outer side. So you will have the secondary turns, okay, sandwiched between the two half primaries. Okay, so having 26.6 linear turns, and we only be needing 25, which is half of 50, it will be half the primary. So in 26.6 and having only to wind 25 tenths, now we know that it will fit in one layer over here. Okay? And considering also the window space we have left, one also can see, if one can see it clearly, we have some clearance left, because when I measured from here, from this side to here, I found about 5 millimeters, and having a clearance of about half a millimeter more on each side, I know that I have around 5.5 millimeters of window space to cover up with the windings in here. Okay, so I'm making sure all the time that what I'm going to do will actually fit in the transformer, because it's useless trying to put thicker wire and needing more turns. You have to consider everything with all the stuff around, because finally when you wind the transformer, having insulating tape maybe between windings and stuff like that, you end up with too much a thicker window here, and this thing won't fit in when you end up with your windings. So we have to be careful and consider all these things. Okay, I'm taking some considerations about amperes and wattage and what is actually involved. We can see that for 350 watts at 155 volts, we will be needing 2.25 amps. So what I did here, I'm just considering the voltage drop just to show, which is rather negligible. Why? Because the turns needed are a few, and the diameters and length of wire also are a few. So what I considering the turns needed and the length of wire we need for our transformer, all I did, I got the bobbin, I measured up the length, the breadth and the length, all right, added up one side of the window space and on every side, and this side came about 20 millimeters, and this side from here to here came about 18. I done that and multiplied it by 2, and the answer came for every turn, for every average turn, okay, because in the bottom there's going to be less and in the upper part is going to be a bit more. So I took the average to be somewhere in between, and I got the result of for every turn is 58 millimeters approximately. So the length of wire needed here is 58 millimeters approximately times 50 turns, which adds up to 2,900 millimeters, which is equals to 2.9 meters. So that's the total length of our wire needed. I did all this to calculate the voltage drop involved. Well, my chart here gives me the resistance for every 1,000 feet is 16.14. So due to the answer being in foot, I had to convert the millimeters or meters in feet. So we know that approximately 39 inches, all right, is equals to 1 meters. So I did 2.9 meters times 39 to get the thing in inches, the answer in inches. I've been needing 113 inches. I divide that by 12, okay, and my answer came to about 9.4 feet. So 2.9 meters is approximately 9.4 foot. Now I'm going to calculate the voltage drop here. So it's 16.14 divided by 1,000. That gives us 0.01614 ohms for every foot. And then I multiplied it by 9.4, the amount needed for that, and our result came to 0.15 ohms for the whole length of winding. Now calculating the voltage drop here, we got 0.15 ohms, okay, multiplied by the amperes needed, and I got a voltage drop of about 0.338 volts, which one can see it is rather negligible at this current. Why I'm saying this? Because on the chart it says that the 0.6 millimeter wire can carry a maximum of 0.92 amps. So I said to myself, but well, taking approximations and knowing that the length is short and the voltage drop isn't that big, one can overload a bit the wire there and not having such a bad effect on the overall setup. So that's why, and that's the reason I settled for 0.6 amperes. Okay, so considering all this, we're going to have from previous calculations, we're going to have one layer, okay, one layer for half the primary in the bottom, and another layer at the very top, okay, on top of the secondary winding. So considering all this, now we come to calculate what we need for the secondary turns. Now for the secondary turns, I decided to make a bifilar winding. The reason for this is due to having more current, and due to that we need a couple of wires side by side so they can handle the load more comfortably. Okay, now coming to the secondary turns, we can do it by proportion. First of all, we have to leave some headroom for the power supply to regulate, and above that we have also to compensate for the voltage drop in the rectifier being on the secondary part. So it's going to be around 2 volts more or less, so having a total extra voltage of around 6 volts, so that due to voltage drops and inefficiencies in the power supply itself, there will be some voltage left to regulate to 24 volts. So we have the secondary turns needed, which is 24 volts, and adding around 8 volts to it, okay, we have a final voltage of 32 volts. Now by proportion we can do this simple sum here. So for 155 volts we need 50 turns. For 32 volts we need how many? So we multiply 32 by 50 and divide it by 155. And the answer comes here to 10.3 turns. Now 10.3 turns won't fit because we can do partial turns in a transformer. So I try to lessen the voltage a little bit, instead of 32 making it 31. Okay, and the same sum give me 10 turns exactly. So instead of 8 volts I will be having 7.5 volts of headroom, which will also suffice. Right, I am also adding an auxiliary winding of 16 volts. Again, this is a nominal of 12 volts plus 4 volts headroom. Okay, due to the same reasons, due to rectifier and the power supply lessening out the voltage to 24 volts, it will stabilize to around 12 volts or so. And the amount of turns needed for this winding is 5.16. Now I am going to round that to 5 turns in all. So that would be our turns needed. So we need 10 turns for 24 volts and 5 turns for the 12 volts needed, which is actually half of this one. Okay, because 12 volts and 24 volts, one being 16 and the other being 32 more or less. Right, now considering the current in the secondary, we also have to consider and make a compromise here, because at 350 watts divided by 24 volts, we will be needing 14.5 amps. Now the current handling due to the chart was roughly, we gave it about 2 amp of current handling, okay, and dividing 14.5 amps needed divided by 2 will be 7 wires side by side, which is actually quite a lot, and we will be having problems fitting them in the transformer altogether. So what we are going to do? Well, through experience, I have seen 5-volt windings in computer power supplies having a quadruplar winding for handling 5 volts at 20 amperes. So having such a few turns, all in all it's 10 turns, and the length of the wire itself is rather short. It would be less than a meter altogether. And having 4 of them at one go, side by side, the voltage drop and the current handling will rise up considerably, and I'm going to consider that my windings is going to be a quadruplar winding, okay, for the secondary turns. And I am going to explain how it's going to be done. Okay, considering the bobbin length and having a quadruplar winding, okay, the bobbin length is 60 millimeter and the wire thickness is 0.6. So we we multiply 0.6 by 4 to see the width of the 4 wires side by side, which is 2.4 millimeters. Okay, so if we divide 60 millimeter, which is the bobbin length, divided by the width of the 4 wires, we can scrounge in about 6.4 turns. Now, needing only 10 turns, okay, we can put a layer of 5 turns and another layer of 5 turns, so we have the 10 turns. Okay, now having our transformer, which is going to be a center tapped one, this will take off the need of putting a full bridge rectifier and having only 2 diodes at the end here with a common anode, and we can put the center tap to ground. Instead of having a full wave rectifier, we can have it with only 2 diodes by putting putting a center tapped winding. So we have to double that. So for 20 turns for the secondary, we'll be needing 10 turns with a center tap in the middle and another 10 turns. So that will add up to 4 layers. Okay? The 50 turns on the primary will have only 2 layers, 1 layer for half of it and another layer on the very top. And for the auxiliary winding, we will be needing 5 turns, and we are going to do it the same way as the other winding over here, and only putting 2 diodes there instead of a full wave bridge. Okay, so that will add up to 1 layer only. So all in all, we will be having, we are calculating the layers needed. Okay, we need 2 layers for the primary, 4 layers for the secondary, and 1 layer for the auxiliary. Now adding up the 7 layers all together and calculating the thickness, okay, by 0.6, which is the thickness of the wire, we end up to about 4.2 millimeter of height. And knowing that the window space we have from here to here is around 5 or maybe a bit more. That will probably fit in very neatly, and it also leaves some room for some tape in between the windings and stuff like that to insulate the windings from each other, and also gives room for some tape, and the window space will actually be all occupied. Okay, one has to be careful not to make a lot of tape here and there, because every time you go around with the tape, it takes 0.1 or 0.2 of a millimeter, and one has to be careful while winding. The maximum attention has to be taken to insulate properly the primary from the secondary winding, okay? And it is advisable also to make this transparent tape we use at home between each winding, just to insulate one winding and not having a lot of thickness. Okay, so that brings our final calculation to our transformer. Right here is a cross section of our transformer, which having half a primary on top, then half the secondary from here to here, again half of the other secondary, and half of the primary. As you can see, the secondary winding is sandwiched between the primary windings. Okay, these lines here illustrate insulating tape between windings. Okay, and it will even help you out during your winding to see more clearly what you are doing. Here is a view of the copper wire chart. One wants to take a look, you can refer to this one. I will also give a link where you can find this chart. Going up again. Okay, here we have an arrangement and possibilities that one can have with the transformer I have explained. Here is a brief description of the primary and the output transistors, with the small capacitor here, the 1 microfarad usually found, and this goes to the center of the bulk capacitors, and providing here on this line about 155 volts, and this goes to the floating voltage anyhow. But this is the arrangement with the diode explained, one with the common anode and putting one on each side, putting this to ground here, and here we have the positive output with the output choke here, a capacitor, and a smaller output choke and another capacitor. Usually this arrangement is found in most computer ATX power supplies. So here we have the output at 24 volts regulated with about 14 amps, coming up to about 350 watts of power. The second arrangement I'm describing here is this one is explaining the same transformer, but instead of having a common anode diode, having a full bridge rectifier, okay, which is then coupled to the ends of the transformer with the center tap being grounded, and the negative voltage here and the positive voltage here. I'm explaining here that the choke, the output choke, is wound on a single ferrite ring, okay, and these are both wound together in a bifilar fashion, and having the output capacitors here and another two small chokes, which only a piece of ferrite, about 3/16 of an inch, well, 5 millimeter maybe, and a few turns, maybe 6 or 8 turns around it. That's all that is here, but it provides a second filtration here and a couple of two output capacitors. Okay, now we're having plus 24 volts and minus 24 volts with a common ground. The output power in this configuration is 48 volts, Okay, plus and minus 48 volts. Sorry, plus and minus 24 volts, which add up all together 48 volts, but with a current handling of around 7 amps, which also brings up the power to 350 watts. So that's the other possibility that can be arranged with the transformer. I hope this video had helped you a lot with figuring out how it is calculated. Okay, so thanks a lot and thanks for watching.